Okay, so we are going to pick up where we left off on our circular motion worksheet, and something that I need you to refer to is this Jamboard. This link here will take you to how I solve the problems, which you'll see me do in this video. So we already covered all this in class the other day, and we're picking up on lesson 3.6. All right, here we go. Lesson 6. All right, so if I were there, we would have done this opener and we would have discussed which direction the rock would fly off. So if a rock was being twirled counterclockwise, if she let go of the object spinning on a string, which direction would it fly off? It would fly off in a straight line tangent to the circle. So the pathway it would take would be D. So D would be the correct pathway that it would fly off because it does have a rotational inertia in that direction of D. And so you would see it going that way. Forces at work. So when things are rotating, there's some forces at work, and the speed of the object along that tangent line involves inertia and momentum. So if it has more mass, it's going to have more momentum, it's going to have more inertia and want to continue in that tangent line. So it has that inertia of wanting to continue in that tangent line. And then there's this force of tension on the string. So as you're spinning a rock or a ball on the end of a string, there is tension pulling that's on that string. And then there's also an attractive force that's pulling the rock toward the center. So my hand would be pulling that back and outside of that tangent line. So that's what keeps it going in the circular motion as opposed to flying off in a tangent line. It would be being pulled back by my hand. And if I were there, I'd be demonstrating so you could see that. We'll look at it when I get back before we take the test on Thursday. All right, then the centripetal force. This is a center-seeking force. So in this case, it would be that that tension on a rope being pulled. That would be acting as the centripetal force when you're spinning a ball on the end of a string. It would be the tension would be working as the centripetal force to pull it into the circle. Whenever the moon is orbiting the Earth, that center-seeking force is gravity. Okay, so there is some kind of force that's being applied to pull it around into that circular motion. So it can be, that centripetal force can be a different thing depending on how it's done. So it is a pull. Centripetal force is a pull that can cause an object to be pulled from its straight line path to curve around towards the center. So it can be tension, it can be gravity, it can be electrical attraction, and then atomic forces in the nucleus. Those are things that can pull it from flying off in the tangent and back into the center and keep it moving in circular motion. The centripetal force acts perpendicular to the direction of travel. So remember, you have that tangential movement, that inertia going on that tangent line. But then you have a center-seeking pull, which acts in perpendicular direction from that travel. And many of you probably have ridden a ride similar to this. And if you've ever ridden it and you're a person on against the wall, you feel like a pressure that feels like you're pulling away from the center. And it feels like you're pulling again away from the center of the thing and being pushed against the wall. And so that's a fictitious force that people sometimes call centrifugal force. So we're going to do this demonstration on Thursday when I get there, and I'll kind of explain that. But it is a fictitious force. People think it's called centrifugal force, and you'll be asked about this. It is a fictitious force, meaning it's not real. this fictitious, it's like used to explain that feeling that we get from riding that kind of ride, that you feel like you're being flattened up against the wall. And they try to explain why the water stays in the bucket whenever I spin it upside down over my head. Again, it's fictitious because it's not real. It's not a real force pulling away. So what is actually happening? Because it does feel like it's being, your body's being pulled towards the wall, or that the water is staying in the bucket. So what that actually is tangential force. And basically it is inertia. It's inertia of your body wanting to continue in the line it's being thrown in, or the water's tendency. If I were to spin a bucket of water over my head, it's the water's tendency to continue along its inertial path that I threw it up. It wants to continue up. So it'll keep moving up until the bucket pulls it back around. So it actually feels as though it's being pushed back against the bucket. Sorry, the trash man's coming to pick up our trash, and you could probably hear that. All right. So there is a calculation here to measure centripetal force, and that is going to involve mass, because it's involving inertia and it's wanting to continue on its path. So centripetal force is going to be mass times tangential velocity squared, and then divided by the radius of the circle. Then we have centripetal acceleration, which you will need to calculate in the test. So we'll do a practice one now. So remember that acceleration is change in direction or speed, and velocity is constantly changing when you're in circular motion because the direction is constantly changing. So centripetal acceleration is the rate of that change of tangential velocity. So that's that tendency to want to go on the tangent. So to calculate that, you'll need to take your tangential velocity, which is represented as vt, and you'll square that, and then you'll divide it by the radius of the circle, and we'll calculate centripetal acceleration. So when a person goes upside down on a roller coaster, what keeps them from falling out, besides the seat belts, okay? So what keeps the train from falling down on that track? So it's centripetal acceleration. In order for it to stay on the track, centripetal acceleration must be greater than the acceleration due to gravity. Okay, so in order for that to stay on the track, centripetal acceleration must be greater than or equal to acceleration due to gravity. So if we remember that acceleration due to gravity is 9.8 meters per second squared. So therefore, we can calculate what the minimum velocity the train must be going to prevent them from falling off the track. Okay, so we're going to see here, we'll see that that radius is 12.2. And I'm going to go ahead and open my Jamboard here. And hopefully it'll flip over. It doesn't want to. All right, well, I'll just do it small then. This is bad. It's backwards. Let me close it. All right, Jamboard, open the right direction. There we go. All right, so I'm going to show you how I calculated that here. So remember that centripetal acceleration must be greater than or equal to 9.8. So we're going to say that the centripetal acceleration is going to equal 9.8 meters per second squared, because that's the minimum speed we're looking for. And so we're going to plug 9.8 into acceleration, into centripetal acceleration. And then we'll use the rest of the formula, which is tangential velocity squared divided by r. So we're going to rearrange the formula because we're looking for the minimum velocity. And so to rearrange it, we're going to do velocity equals the square root of 9.8 times r. So this is my rearranged formula right here. Okay, so centripetal acceleration is going to equal 9.8. I'm going to rearrange it, and that's the formula we're using right now to find our minimum velocity. So velocity is going to equal the square root of 9.8 times r. If you can see here, r is this 12.2, and that's what we're going to use. Okay, so r is 12.2, and v equals 9.8 times r. So we'll plug that 12.2 in, and we've got the square root of 9.8 times 12.2, okay? And so we're going to multiply that. I got 119.6. Take the square root of 19.6, and that gave me 10.9 meters per second. And that is the minimum speed the roller coaster can go, is 10.9 meters per second. Now, there is a question like this on the honors addendum, so you do want to make sure you review this and know how to calculate a minimum speed. All right. And we'll go back to the slides. All right. That does... centripetal force does play a role in planets in orbit. We'll look at that later on in the year. There is some calculations in your lesson about center of gravity, and you can usually use these formulas that you see here to calculate uniform shapes. So those formulas will be in the lesson, so you can calculate those. Sometimes you can, in order to find the center of gravity of an irregular object, you can use a plumb bob, which is basically you're hanging a string and letting gravity make a straight line. And then you'll turn the object and draw another straight line, and then you'll see where the dots intersect, and the lines intersect, and that's going to be the center of gravity for an irregular object. How center of gravity affects stability. Now, higher centers of gravity will be less stable. Lower centers of gravity will be more stable. So I usually like to do a demonstration here and show, because men tend to have a higher center of gravity than women. And yes. And then also taller people have a higher center of gravity than women. And then I show a demonstration of a person on a high wire and how they use a stick that has weights at the end, and it shows it like lowers their center of gravity to make them more stable. Also, if I were there in class, you'd see me standing on my head. I do a headstand and show you how I demonstrate a wider base of support over a smaller base of support to balance in a headstand, and how I would teach my gymnastics class that. So higher center of gravity is less stable, lower is more stable, smaller base of support is less stable, wider base of support is more stable. This is kind of involving rotational inertia, and this and center of gravity also kind of have to do with this. So objects in rotation around an axis tend to remain in rotation about that axis until acted on by outside influence. So when a mass is toward the center, it has low rotational inertia, meaning it can change more easily. And when the mass is toward the outside, it can change, it's harder to change. That means that once it's in motion, if it's spinning and it has more mass on the outside of the farther away from the axis, it's going to be harder to stop it as well. Okay, it takes longer to start, but it also means it's harder to stop. So I have a friend who he spins sabers, and he spins, I don't know what they are, staffs. He spins staffs, and he'll get them weighted at the end so it can continue the rotation, and when you throw it, it rotates better and it doesn't like stop rotating. So if the weight is towards the center, it's less likely to continue in the rotational motion, but it is harder to get it spinning if it's weighted on the outside, but it's harder to stop it spinning as well. Does this video work? I don't know how to play the video. Apparently I can't. Do I need to push present or something? Play present on this device. Oh, maybe I can play the video. Ah, yay, okay. So we'll watch this ice skater spinning. You can see how she's spinning at a certain pace, and then when she pulls her mass in closer, it spins a little bit faster, and even faster when she closes in and pulls in. So remember, when mass is closer in, it's easier to spin the object. So when R decreases, velocity increases. And that's angular momentum. All right, let's look at rotational inertia formula. So to calculate rotational inertia, I is for inertia, and it equals mass times the distance squared. And the distance is usually the radius. All right, we'll play this video. He shows a demonstration here.
We're going to look at a couple more demonstrations of rotational inertia. Now, to review, rotational inertia is the property of an object that deals with a resistance to a change in its state of rotational motion. We know that this depends upon the mass of the object and the way that mass is distributed from the axis of rotation. For the first demonstration, let's look at this aluminum disc.
I'm going to go forward and we'll look at these two rolling discs. So these two rolling discs that he's showing you.
Is an aluminum ring, and the other is a piece of wood. Now, if these have the same mass, they have the same inertia, but they don't have the same rotational inertia because that mass is distributed in a different way. For this, the mass is distributed uniformly throughout. For the ring, the mass is all distributed far from where the axis of rotation will be, which is going to be right through the center. And so this will have a greater rotational inertia than this wooden disc.
So that means that it should take longer for it to start,
race down this incline,
and it should continue rolling.
And the one with the greater
higher
rotational inertia will lose the race because it will have a greater resistance to a change in its state of rotational motion. Now, right now, the state of rotational motion of both objects is 0. They're not rotating. Once I remove the piece of wood, one of them is going to rotate more quickly. Let's see which one that is.
So also, if it were to continue rolling, so you saw the one that had more rotational inertia takes longer to get started, but it is also harder to stop. So it should also continue rolling farther than the wooden one. So although it takes longer to start, it should continue rolling farther. Okay, I do have some math practice here, so let's go back to the Jamboard. Okay, so the question was, which has more rotational inertia, a dumbbell with 2 meters wide or with 3 kilogram masses on each end, or one that's 4 meters wide and 3 kilogram masses on each end? So the two dumbbells have the same mass, 3 kilograms. And then, but one is twice as long as the other. So this is 2, this is 4. All right. So we've got 3 kilograms and we've got 2 meters wide. So let's look at that. So our radius from the halfway point is going to be 1. Okay, so we've got 1 squared, and then, I equals md. Mass is 3 kilograms is the mass, times the radius squared, which is 1 in this case, 1 squared, equals 3 times 1 squared. 1 times 1 is 1. This is going to be 3 times 1 is 3, and it's kilogram meters squared, which is newtons. All right, and then this one, the radius is 2. So we've got 4, sorry, not 4, 2, 3, mass. The mass is still 3. And then we've got times the 2r, or 2 squared meters. Let's do it this way. 2 meters squared. There we go. And that equals 3 times 4 is 12. And that's newtons, because it's kilogram meters squared. So you can clearly see that the one with the larger radius will have higher inertia, rotational inertia. All right, finally we have this last calculation. All right, so it's everything we've gone over in circular motion. So Missy's favorite ride at the fair is a rotor, which has a radius of 4 meters. The ride takes 2 seconds to make 1 full rotation. What's the distance she travels in 1 rotation? So if we remember that distance is going to be equal to the circumference, okay, so if she's here, to make 1 full rotation, she's going to go the same distance as circumference. So distance equals 2 pi r. R is 4, so we're going to do 2 times 3.14 times 4, and we'll get our rotational distance. Times 3.14 times 4. Sorry. There we go. 25.12. And then, so we're going to use this again because that's your distance, and we're going to use that when we calculate that. So let's go here. Let's change colors. So now we're going to calculate W, which is our rotational speed, and that's the number of rotations over time. It says 1 full rotation in 2 seconds. So it's going to be 1 over 2. We got that as 0.5. And that equals W, which is our rotational speed, and that's rotations per second. All right, so now we're going to go, our distance here is meters. Our distance times our rotational speed will give us our tangential speed. Let's change our color again here. So tangential velocity equals D, which was 0.5 RPS, times 225.12. Oh, no. Yeah. Yes. Okay, so that's going to give us VT. So 0.5 times 25.12. And that does not look right. There should have been a decimal point there. Let's see. 225.12 times 0.5. There we go, 12.56. Oh, that's in green. Let's do green for that, 12.56. And that's our tangential speed or tangential velocity. So now we're going to plug this in to here. Okay, so now we're going to find Missy's centripetal acceleration. Okay, so we're going to plug in VT, and that's 12.56, and that's going to get squared, and that's going to be divided by the radius, which was way back when we found the radius over here. So divided by 4. Okay, so we got to do 12.56 squared. Let's see if this thing will let me do that. 12.56 squared. Nope, that didn't do it. Nope. Sometimes technology isn't as great as you think it's going to be. 12.56 times 12.56. There we go. 157.8 divided by R. I think that was right. Yeah, and the R is 4. 39.45. And then we do that yellow. All right, so those are all of the notes for today. Oh, hold on, what's the unit on this? Centripetal acceleration is meters per second squared. This is meters per second. There we go. All right, so this is the end of my notes, and hopefully you guys can answer the questions in Jupyter and get everything right 100%. And I will see you guys on Thursday. We'll review for the test. Oh, don't forget the math practice is due to, you got to get that done before the test so you're ready for all the math problems that are on the test. They are word for word, the questions that are on the test with different numbers. So make sure you do them, and I will let you use that. If you do it on paper, I will let you use that paper during the test. You guys have a good day. I wish I could be there with you today. I'll see you on Thursday.